So in the last class, we did problems using double integration. The basic formulations we did, and then problems of how we use an integration strip to do integration of areas, how we can find areas using double integrals. And also we can find volumes of revolution using double integral. So now before we move to triple integral, there are one or two problems on volumes. So we will do volumes of solid of rotation using double integral. This question 4, we have done 3. The upper half of the cardioid R is equal to A into 1 plus cos theta rotates about the polar axis. What is the polar axis? This is the initial line. Find the volume generated. Find the volume generated. So, how to do this problem? First, draw the initial line. This is a perpendicular line. All right, this is theta equal to 0, theta equal to pi by 2, theta equal to minus pi by 2, theta equal to pi. The same line as theta equal to minus pi if we go the other way around. This is the pole. Now cardioid, when theta equal to 0, cos theta is 1. So R will be equal to 2a. And when theta equal to pi by 2 or minus pi by 2, cos theta will be 0. So R will be equal to a. So when theta is pi by 2, the distance from the origin will be half of this distance. So this will what be. And when theta equal to pi or minus pi, cos theta will be minus 1. So R will be 0. So R will be 0 when, so what we get, the shape of the cardioid will be like this. So this is the shape of the cardioid, and this is rotated about the initial line. So now R at any point R, sorry, this is R, this is theta, this length is R sine theta. Okay. Now, how to do that? How to choose? What we do is actually we, instead of choosing any point on the circumference, to find the volume generated, you have to do area multiplied by the circle of revolution. So we have to take an area element. We take an area element. Okay. Now this area element we know is r d theta dr. R d theta is this dimension and dr is this dimension. This is the area element. We have done that. This is d theta and this is theta. Now this area element will be at a distance of r sine theta from the initial line. So when you revolve the cardioid area about the initial line, what happens is this r, so the circumference of revolution of this element will be 2 pi r sine theta. R sine theta will be the radius. Okay, because this element will be revolving around the initial line. So 2 pi r sine theta dA. This we have to integrate with respect to A. Okay. So this will give you volume of revolution. So how do we do this? This is 2 pi r sine theta times r d theta dr. So now this is a double integral. So now 2 pi r square sine theta d theta dr. Now r is varying from 0 to, along any line, you see this area element has to vary along r. So r varies from 0 to a into 1 plus cos theta. So you get r equal to 0 to a into 1 plus cos theta. And theta will vary from 0 to pi, because just take the upper half. Theta, at this point theta is 0, at this point theta is pi by 2, at this point theta is pi. So theta equal to 0 to pi. Okay, this angle theta, all the area elements in the upper half we have to consider. So theta equal to 0 to pi, integral r equal to 0 to a into 1 plus cos theta, 2 pi r square sine theta d theta dr. So first is integral with respect to r. So volume will be first integral 0 to pi, treat all others as constant. So 2 pi sine theta is constant. Then integrate r square with respect to r. Okay. I'm writing step for your reference. I would directly solve it. Okay. Now this will be integral 0 to pi 2 pi sine theta to r cube by 3. So, and substituting the limit, we get a cube into 1 plus cos theta, the whole cube by 3 d theta. Okay, applying the limits. So now here 2 pi a cube upon 3 is taken out, and 1 plus cos theta the whole cube into sine theta d theta. Now substitute cos theta equal to t, which implies minus sine theta d theta is equal to dt. And see the limits, theta to t transformation. When theta is 0, t will be 1. And when theta is pi, t will be minus 1. So v is 2 pi a cube upon 3 integral 1 to minus 1, 1 plus t the whole cube into sine theta d theta will be minus dt. So this minus it will remove the sign of the integral. Sorry, it will remove the, it will change the limits. It will change the limits of integration. And now when you integrate, you get 2 pi a cube upon 3 times 1 plus t whole power 4 upon 4 minus 1 to 1. This will be 2 pi a cube by 3 into 2 to the power 4 minus 0 by 4. So 16 by 4 is 4, 4 2 is 8. So 8 pi a cube upon 3. This is the volume. Okay, so we have taken an elemental area, revolved it, and then integrated over that area. This is the volume of revolution. This is for a polar coordinate, volume of revolution. So the concept lies only here at this step, how you do it. After that, this is all about evaluation of double integral. Okay, just that concept we'll have to use. Next part, find the volume of x square by a square plus y square by b square plus z square by c square equal to 1. What is this? This is called as an ellipsoid. Okay, you put z equal to 0. That means in the xy plane, it will be an ellipse. Then you put y equal to 0. In xz plane, it will be an ellipse. Put x equal to 0 and yz plane, it will be an ellipse. So any plane you cut through, it will be an ellipse. So how to do this? So it is a solid body. To draw will be very difficult in 3D. Extremely difficult to draw in 3D. Meaning we can use a 3D grapher to draw it, but x, y, z. So this will be point A minus A, B minus B, and C minus C. This is in one plane, but this will be a solid. It will be a full solid body like this. So what we do, we write z as a function of x and y. That we can write. In fact, there will be two parts. Z will be plus or minus c times under root of 1 minus of x square by a square minus of y square by b square. The plus sign tells the portion of the volume lying above the x-axis. The minus sign is the portion of the volume below the y-axis. So okay, so now when you have to integrate, now let us look at the x y plane. XY plane. In the XY plane, let's say this is the ellipse. So this will be x square plus a square plus y square by b square equal to 1. Because here z equal to 0 on this plane. So how to integrate? If we have to integrate using double integral, of course, by using single integral, we can integrate this. But here it is a volume problem, integrating for volume. Double integral of z dx dy. Now z, let us see how it now I will use only the upper half. So then I have to multiply it with 2. If I have to use the upper half, I have to multiply this with 2. So I get integral. It is like finding the volume of this solid of revolution. This is the dx dy. All right. You revolve about the x-axis. So now y will vary from, let us do this. All right. So we have y will vary from, if I have to revolve like a solid of revolution, then y, I can just write y as from 0, from this part to b by a under root of, take this to the other side, a square minus x square. Okay, y is plus or minus b by a under root of a square minus x square. All right. Z is c times under root of 1 minus x square by a square minus y square by b square. Now dy dx. Now x will vary from minus a to a. X varies from minus a to a, but y varies from here to here because I am doing a, no, I'm not doing a solid of revolution. If I do a solid of revolution, I have to do 2 pi r. I'm not doing the solid of revolution. So in that case, wait a second, then I will do this. This is x is equal to 0 to a. Whatever this volume I find here multiplied by 8 times. Suppose in 1 octant, I am finding the volume that multiplied by 8, not just 4. In a quadrant, it will be multiplied by 4. But the volume, it's on the upper side and the lower side. So this multiplied by 8 will give me the volume. So what I'm doing, I am taking 0 to A and 0 to this point B, of course. Now, when I integrate this, now this is Z. It is not just Z times dx dy. I automatically get the volume. Now, what to do? How to do this? So first integral is with respect to y. So this is 8 times integral 0 to a. Now c you take outside. Now integral of a square minus y square. That's how you have to treat this problem as a square minus y square. So the way to do this is it is x by 2. So x is y upon b, x by 2, x by 2 into under root of a square minus x square. So this as it is, then plus the a square by 2. This is this formula. So instead of x, you have to take y by b, and instead of a, you have to take this whole expression. That's what we are doing. Plus a square by 2 sine inverse x by a. Now this is from 0 to b by a root of a square minus x square. Now this will be dx left. Now if x is replaced by kx, then the whole integral will be 1 upon k. So 1 upon 1 by b will give me b, right? Because of this coefficient. So this is very careful. We have to do the integral for this. So this is like 2 to take 2 and 2 common, bring it out. And so it becomes 4 bc integral 0 to a. Now look at this stuff. Substitute y as, when you take this whole thing inside, yeah, when you take this whole thing inside, it is, see, y is this. This is rough area. So y is, instead of y, we are substituting this. So y by b whole square will be 1 by a square into a square minus x square, which is 1 minus of x square by a square. So when you substitute y here, it means that y by b the whole square is equal to 1 minus x square minus a square. So when you substitute this here, it becomes 0. So first term is 0 plus the second term, a square minus x square by 2a square times. Now this becomes y by b. Y by b is under root of 1 minus x square by a square. So y by b is same as this when you substitute this one. So you'll get sine inverse 1. Sine inverse 1 is pi by 2 minus of, substitute this limit, instead of y, this becomes 0. Just a second. Getting message that internet is unstable, so I'm just adjusting. Internet, yeah. I think now it will be stable. So put y equal to 0, this whole term will be 0, and put y equal to 0, your sine inverse 0 will also be 0 dx. So now we are left with pi by 2, we can pull out completely. So pi by 4, in fact, so 4 cancels. We have pi bc upon a square to integral 0 to a. A square minus x square dx. So we get, I'm just seeing whether we done right. Yeah. So pi bc upon a square into a square x minus x cubed by 3 from 0 to a. So pi bc by a square into a cube minus a cube upon 3. So we get 2 by 3. So 2 pi a b c by 3. Let me just see. I made a mistake somewhere. Yeah, the mistake I made is I pulled out this 2, but here I retained the 2 because if A equal to B equal to C, you should get 4 by 3 pi r cubed. That is the volume of the sphere. So here the mistake that I made is that this remains 8 here because I'm retaining this 2 here. If I didn't retain this 2 here, if I had already cancelled, that is different. So I have just retained 8 BC and I've maintained everything else as it is. So 2 into 2, 4, this becomes 2. So this becomes 2 here. So this is 4 by 3 pi ABC. If A, B, C are equal, then it will be a sphere. So 4 by 3 pi r cube. Okay. One more small question before we go further. I'll give this as a homework anyway. It's a simple problem. Given in one of the previous papers. So that anyway is a homework sheet I've already attached to that. So now what we do is we'll go for triple integral. Now let's work with triple integrals. Just like the double integral. Now triple integral, it's not just talking about volume, it's a more higher dimension. Triple integral of f of x comma y comma z dv. This will be over volume. So this is defined as limit n tending to infinity and delta volume tending to 0 sigma f of xr yr zr dvr r equal to 1 to n. That means the whole volume. Now this is a function of 3 variables. So the function exists in the 4th dimension. X, Y, Z are variables. So the function itself, the value of the function has to be plotted in the 4th dimension. So this is difficult to conceive by our human vision. Now, function value multiplied by a volume element. Volume element will be dx, dy, dz. So this integral, the working rule is like this. So the working rule is this integral over volume of f of x comma y comma z dv will be equal to integral of x comma y comma z. First integrate with respect to z, then with y, then with x. Now z will be some function z1 of x comma y to z2 of x comma y. So we are integrating with respect to z, treating x and y as constants. And then we substitute whatever the functional expression is, z in terms of x and y. Then next, we integrate with respect to y, and we write y as a function of x. So y1x to y2x. And finally, x will vary between two constants. Of course, depends on your volume element, how the volume element is. If the volume element is constant between the planes uh, x equal to x1 to x equal to x2, then this is how we do it. Of course, from problem to problem, we have to change this. Now, how to evaluate volume of a solid by triple integral? So, volume of a solid using triple integral. How do we do? Now, dv, this dx, dy, dz itself is a volume element. Now, if you put f of x comma y comma z dv, then it is volume times some other dimension. So it will go, the dimension will go greater than the volume. So this itself is the volume element. So to find the volume, we take the volume element dv and integrate that dv. So we can write this as 1 times dv and integrate with respect to the volume. So we get a triple integral like this: 1 times dz, dy, dx, or anyway, any order you want to choose, whichever order you integrate first, that should be a function of the other two. Second, if you integrate with respect to y, then y should be as the function of x. And finally, this one. So this is how we find the volume. So some common problems of this type in GATE. So example problems that we'll do now. First, evaluate I is equal to integral -1 to 1, then integral 0 to z, and integral x minus z to x plus z, x plus y plus z, dx, dy, dz. Now look at the limits. Based on the limits, you have to judge the sequence of integration. The first limits are the functions of x and z. That means first we are integrating with respect to y. Y is a function of x and z. So integral -1 to 1, integral 0 to z. Then this is integral, this is y, it is not mentioned, but y is lower limit is x minus z and upper limit is x plus z of x plus y plus z dy. So first we are integrating with respect to y. Then it is from 0 to z. That means next it is integral with respect to x. Then it is integral with respect to z. Understand? First it is y. Then it has to be between x and z, right? Y function is over. So between x and z, z is there. So this means x is a function of z. And the last one will be z remaining. So now first we integrate, say minus 1 to 1, integral x equal to 0 to x equal to z, and integrate this part with respect to y. So treating x and z constant. So if we treat x and z constant, we'll get x plus z times y, and treating y, integrating with respect to y, y square upon 2, 0 to z, dx dz. So next we'll integrate. We'll substitute the limits now. Put y equal to z here. So you get x plus z times z plus z square by 2
Sir,
minus of
limits are x minus z.
sorry. Thank you. I made a mistake. I didn't see this. Thank you. The limits are x minus z to x plus z. So let us substitute. So when you substitute y is equal to x plus z, we'll get x plus z the whole square plus again x plus z the whole square upon 2 minus, substitute here, x plus z into x minus z will be x square minus z square minus x minus z the whole square upon 2. All right. So dx dz. Now we'll have to simplify this. I'll simplify here instead of doing the full calculation. So this is 3 upon 2 x plus z the whole square. X square plus z square. X square plus z square plus 2xz. Now minus x square plus z square. Then minus x square by 2 minus z square by 2 plus xz. This term. So we have 3 by 2 x square minus x square by 2. So this is minus 3 by 2 x square. So that cancels. That becomes 0. 0 x square plus, let's see z square term, 3 by 2 z square minus z square by 2. That will give us 3 by 2 minus 1 by 2 will give us 1. So 1 plus z square. So I'll get 2z square. Okay. And then xy term. So 3 upon 2 times this will give you 3xz plus 4. 3 plus 1, we are getting 4xz. So this will be the simplification. So 2z square plus 4xz. So this is integral minus 1 to 1, integral x equal to 0 to z. We are left with 4xz plus 2z square. Now we integrate with respect to x and then with z. So y is gone. So now we have to integrate with respect to z. So this will be 4x into z square by 2, that is 2x z square plus 2z cube. Oh, no, I'm doing with respect to x. I'm sorry. So I'll get 2x square times z plus 2xz square. X varies from 0 to z. So upon substituting, I get, instead of x, I have to put z minus 0. No, z. So 2z cube plus 2z cube minus, substitute 0, minus 0. So this is minus 1 to 1, 4z cube dz, and it's an odd function. From minus a to a, it is 0. So after all this calculation, the value of this integral is 0. Okay. So this is how we evaluate a triple integral. All right. So we need to be careful how we apply the limits. That is the okay, volumes. Next, volumes. Volume of a cube is easy. That I'll anyway give as a homework exercise from the exercise sheet. Look at one question. This is question 4 from the exercise sheet given to you. Evaluate. This kind of questions are very important. Evaluate triple integral 2x plus y dx dy dz, where V is the closed region bounded by the cylinder z is equal to 4 minus x square and the planes x equal to 0, y equal to 0, y equal to 2, and z equal to 0. So how to do this problem? Main step is to conceive the problem. If you conceive the volume, after that, you will be able to do. First thing is, this is a curve in xz plane. That we should be clear about in xz plane. So first let us plot x, y, z properly. This is x, this is y, this is z. Okay. Now this is a curve in xz plane. if we remember this curve, like if you remember the curve y is equal to 4 minus x square in the xy plane, this is a parabola. Parabola which opens, yeah, you know, x square, it opens downwards. All right, it opens downwards. The maximum value of this parabola is 4. This y will, so it will be 4. So if we remember this curve, this will be like this. At x equal to 2 and x equal to minus 2, the value of y will be 0. Okay. So similarly, z is equal to 4 minus x square is a parabola like that. This is 4 and this is 2. Now, this is bounded by the planes x equal to 0. X equal to 0 is the yz plane. So this particular plane, it is bounded. All right. So that's why I've drawn only up to here. So x equal to 0, y equal to 0 means here, and y equal to 2. So at y equal to 1 and y equal to 2 at this plane. So I'll draw it accurately as possible. Hmm. So this will be the volume. I'll draw the dotted lines carefully so that you. So this shaded portion is bounded by, see, this is y equal to 0 plane, xz plane. All right, xz plane. And this particular portion from the behind, this is y equal to 2 plane. Okay, this is parallel to the xz plane. So a cylinder cut by y equal to 0 and y equal to 2 planes like this. And then it is also bounded by x equal to 0. That means this yz plane. All right. And z equal to 0. So z equal to 0 is the xy plane. So the bottom plane is z equal to 0. This plane is x equal to 0. So it is bounded by 1, 2, 3, 4. So this is the volume that we need. Okay. In fact, you can say that I need this region in the positive octant. This is not mentioned, but it is volume in positive octant. Positive octant means all x, y, z are all positives or 0. So this is the volume we need. Now here we choose any volume element. Z varies from z equal to 0 to z equal to 4 minus x square. All right. Now x varies from 0 to 2. This is 4 on the z-axis. This is 2 on the x-axis. X varies from x equal to 0 to x equal to 2. Y varies from y equal to 0 to y equal to 2. So this is given straight away. This we have deduced. Okay, it is not directly given. And this is given anyway. So now we have to evaluate this integral. So I is equal to integral of triple integral of 2x plus y. First, we will integrate with respect to z because z is a function of x. Then we can integrate with respect to y or with respect to x because both are constants. The limits are constants. Doesn't make a difference. So we'll do dx dy. So z varies from z equal to 0 to z equal to 4 minus x square. And x varies from 0 to 2 and y varies from 0 to 2. So this integral is integral 0 to 2 y integral x equal to 0 to 2. Now integrate this with respect to z. So 2x plus y will be treated as constant. You get z between the limits 0 to 4 minus x square. So y equal to 0 to 2, x equal to 0 to 2, 2x plus y into 4 minus x square dx dy. So we'll have to simplify this. X equal to 0 to 2. You will get multiply 2x with 4 minus x square. We get 4 into 2, 8x minus 2x cube. So 8x minus 2x cube plus 4y minus yx square dx dy. So now we can integrate with respect to, of course, if we want to simplify, there are no terms, constant, coefficient of x square, coefficient of x cube. So all 4 terms. So we can directly integrate 8x integral with respect to x is 4x square minus 2x power 4 upon 4 plus 4xy minus y into x cube upon 3 applying from 0 to 2. So we get 4 into 2 square upper limit minus lower limit. And for each term individually I'm doing minus half times 2 power 4 minus 0 power 4 plus 4y times 2 minus 0 minus y by 3 times 2 cube minus 0 cube. Okay, so this is integral 0 to 2, 4 into 4, 16 minus, this is 16, 2 power 4 is 16 upon 2, 8 plus 8y minus 8 by 3y. So this is integral 0 to 2, 8 plus 16y by 3 dy. So when we integrate, we get 8y plus 8y square upon 3 from 0 to 2. We get 8 into 2 minus 0 plus 8 by 3 into 2 square minus 0. 16 plus 8 fours, 32 upon 3. So 16 3 is 48 plus 32, that becomes 80 upon 3. This is the integral, not the volume. This is the value of the integral. So the whole problem lied in trying to figure out the volume. What is the right volume? If we are able to draw the figure correctly, after that we have solved the problem. One more of this type. After that we'll move to the next. One more of this type. This is an important one. This is an evaluate x square dx dy dz over the region bounded by x equal to 0, y equal to 0, z equal to 0, and x plus y plus z equal to a in the positive octant. That it is implied. This is implied. I think this, so now you all help me in figuring out how to do this. So let's say this is x, this is y. By right hand thumb rule, z will be here. Okay. Now x equal to 0 is the yz plane. Y equal to 0 is the xz plane. And z equal to 0 is the xy plane. So three planes are, so three planes are dividing this whole space into 8 octants, and x plus y plus z equal to a. So when y and z is equal to 0, x will be equal to a. So this is a point that lies on the plane a comma 0 comma 0. This lies on the plane. Then when x and z are zeros, then y value will be a. So this is 0 comma a comma 0. 0 comma a comma 0. And the last one, zero comma zero comma a, right? So for a line, we require 2 points through which a unique line passes. And if there are 3 non-collinear points, then a unique plane passes through that. So this plane is so this plane forms a tetrahedron with 3 sides perpendicular to each other. And there's a 4th side. Okay. So the volume, the region that is bounded is this region, this whole volume. So this is a tetrahedron. So we can sequentially, we can integrate first with respect to z, then volume element, Now integral when we evaluate, z varies from, we write the limits, z varies from z equal to 0 to z is equal to a minus of x plus y. So z is a function of x and y. So z is taken care. Once z is over, z varies from 0 to this. Once z is over, then y. Okay. Now y will vary. So neglect z, then y varies from, along this strip we have taken from 0 to x. Now y will vary from y equal to 0 to x equal to a minus, sorry, y is equal to a minus x. And then x varies from x equal to 0 to x equal to a. This is how we evaluate the volume. Of course, this let us see, evaluate and see how we get this. So integral, we get this integral, it's of course x square times integral x varies from 0 to a, y varies from 0 to a minus x, z varies from 0 to a minus x minus of x plus y, x square dz dy dx. That's it. So x equal to 0 to a, integral y equal to 0 to a minus x. Integrating this with respect to z, you get x square times z. Applying the limits, we'll get, instead of z, we get a minus x minus y dy dx. So now this becomes x equal to 0. Next, we have to integrate with respect to y, treating all others constant. So x square into a minus x minus y into x square dy dz. All right. Now integrating with respect to y, we get x square into a minus x times y minus y square by 2 into x square. This is dx. Applying the limits of integration for y equal to 0 to a minus x. So we get integral x equal to 0 to a x square into a minus x into a minus x minus 0. So a minus x whole square minus a minus x the whole square into x square upon 2 dx. So the whole thing simplifies to, this is x square into a minus x whole square. This is also the same, x square into a minus x whole square by 2. So this will be x square into a minus x square by 2 dx. Now we can integrate 1 by 2 integral 0 to a square x square minus 2ax 2ax cube plus x power 4 dx. Now this is a square into x cube by 3 minus 2a x power 4 by 4 plus x power 5 by 5. 0 to a. This is 1 upon 2 a power 5 by 3 minus 2a power 5 by 4 plus a power 5 by 5. Let us simplify this. 60 will be the common denominator. So 3 into 20. So 20 a power 5 minus 4 into 15. So 15 to 30 plus 5 12s a power 5. So this is 32 minus 30. So 2. So 2 and 2 cancels. We get a power 5 upon 60. This is the value of this integral. Okay. So this is how triple integrals are evaluated. For finding a volume, you just use 1 into dx dy dz and appropriately choose the element and integrate. Now, a very, very important, very important section. In fact, this is not just limited to triple integral, it is for double integrals also. How to do substitutions. This is extremely important section. Maybe I should treat this as a new section altogether. Now, it is not just change of order of integration. It is substitution of variables. Like we have done in calculus of functions of single variable where limits of integrations change, like so many problems we have done. Say theta is converted to t, then when theta is 0, t assumes some value. When theta is pi, t assumes some value. All right, like cos theta equal to t, we make a substitution, then the integral that was in terms of theta, that converts to t. All right, by the substitution. Now, how to do that for double integral and triple integrals? How does the substitution work? So, substitutions. Or change of variables. First part in double integrals. Substitutions or change of variables in double integrals. So, let the variables x and y be changed to new variables u and v by the transforming functions x is equal to phi of u comma v and y is equal to psi of u comma v. So there are two functions. Okay. So where, of course, these two are continuous functions where phi and psi are continuous and differentiable on this transformed plane. All right. In the UV plane. They are transformable. So then how do we, what is the method of transformation? Remember, for suppose in function of single variables, x was replaced by say phi of t. X was replaced by phi of t. Then dx will be phi dash t dt. So I becomes integral f of phi of t into phi dash t dt. All right. Remember, in single variables, we do like this. So in double variables or function of two variables, this is in the region of xy plane. Over this region xy plane, we are integrating. Now, this is converted to a region in UV plane, and this becomes function of x will be phi of u comma v. Y becomes psi of u comma v. Then what happens to the derivative f dash part? This is multiplied by the Jacobian modulus of the Jacobian du dv. Now we read of Jacobian and partial derivatives. So where J is Jacobian, it is now xy is being changed to uv, right? So it is dou of x comma y by dou of u comma v, because then again you have du dv. This is nothing but the determinant of dou x by dou u and dou x by dou v by dou y by dou u to dou y by dou v. So in brief, we can write this as x subscript u, x subscript v, y subscript u, y subscript v. This is the Jacobian. We use this to transform. We'll not go into the proof of it. We can prove it. It's a lengthy process, but this is the Jacobian. Okay, in transformation, just by multiplying with the Jacobian, we change the variables. Previously, we did change of the order of integration using areas. Don't mistake that. This is change of variables. Okay, clear? So now for triple integral. So in triple integrals, how it would be? Now, if the variable x comma y comma z are changed to u comma v and w by a transformation, x is equal to, say, g1 of u comma v comma w, y is g2 of u comma v comma w, and z is g3 of u comma v comma w. Then the transformation is like this. The triple integral in the region or the domain x, y, z plane of f of x comma y comma z dx dy dz will transform to, very simple, in the corresponding region in UVW space, it will be f of g1 of UVW plus g2 of u comma v comma w plus, I'm sorry, not plus, comma. Instead of x, y, and z, we have this multiplied by the modulus of the Jacobian times du, dv, dw. That's it. You don't have to worry. Just substitute, and this derivative, partial derivative conversion, you multiply with Jacobian. where Jacobian J dou x comma y comma z by dou u comma v comma w, determinant of x differentiated with respect to u, x differentiated with respect to v, x differentiated with respect to w, y differentiated with respect to u, y differentiated with respect to v, y differentiated with respect to w, z differentiated with respect to u, z differentiated with respect to v, z differentiated with respect to w. Okay, so this is, the change of variables and substitution. Okay, this is in triple integral, this is in double integral. Some particular cases, so conversion to polar form and cylindrical coordinates, these are sometimes the Jacobians, they are used in very complicated physics problems, or fluid mechanics or advanced mechanics of materials problems. So particular cases, what we are going to discuss now, this may or may not be asked in GATE as a direct exam, direct question, at least the conversion into 3 coordinates, spatial coordinates, but this will definitely happen from conversion to Cartesian to polar coordinates. So the first case, now conversion of a problem from Cartesian coordinates to polar coordinates. Conversion from Cartesian to polar coordinates, very important, in a plane. In a plane. All right. So in a plane, how does it convert to? So x comma y gets transformed to r comma theta. So x is equal to r cos theta, y is equal to r sin theta. Okay. So what is the Jacobian? Jacobian is determinant of dou x by dou r, dou x by dou theta, dou y by dou r, dou y by dou theta. This is partial derivative with respect to r, you will get cos theta. Partial derivative of x with respect to theta, derivative of cos theta is minus sin theta. Then derivative of y with respect to r is sin theta. And derivative with respect to of y with respect to theta is r cos theta. Now this determinant, you can take r outside. And what we get is r, you have determinant of cos theta minus sin theta, cos theta. So cos square theta minus of minus sin square theta, that is cos square theta plus sin square theta is 1. So Jacobian of conversion from Cartesian to polar coordinates is r. This is the Jacobian. Therefore, if a problem is converted from xy plane to a polar plane in a polar coordinate system, you have to go to the corresponding region in the polar coordinates. Now x will be replaced by r cos theta, y will be replaced by r sin theta into Jacobian r into dr d theta, and which we know by the area conversion which we have done earlier of the elemental area. So area element in the Cartesian plane is dx dy, but the area element in the polar plane is polar coordinates plane is r d theta dr. So that's what we are getting. So conversion from Cartesian to polar coordinates is just by using this Jacobian, just this result. So now conversion from Cartesian to cylindrical coordinates. I don't know whether you know what are cylindrical coordinates. I'll just try to. You must have used it. Okay, this is the cylindrical coordinate system. Polar coordinates in one plane, r theta. Okay, but it has z. So it is like a cylinder. The coordinates are like a cylinder. So this is the pole, this is the initial line, this is theta, and this is z. So in a plane, it will be r theta, and perpendicular, it will be z. So cylindrical coordinates are very, very useful. So this is r theta z along this cylinder. Okay. So three planes here, it is showing the three orthogonal components. Rho means r, green. So as r is increasing, this green cylinder is increasing. Phi is red. So this is the plane. This is the theta plane, and z is blue. So intersection of these three planes will always give one point, and that point is the cylindrical coordinate of that particular point in space. It will keep changing r theta z. Okay, we have full calculus developed over it. Why we have to go through this mathematics? Sometimes in some situations it is very, very useful. So r theta z. Now instead of worrying about how to do conversion of Cartesian coordinates, x, y, z to cylindrical coordinates, r theta z. So polar coordinates are in a plane when z equal to 0. Okay, when that is pulled up along the z axis, it will be like a cylinder. So now Jacobian. So what is the relation? X is r cos theta. Y is r sin theta in this case. Now this z is z. So no change. Z coordinate remains the same. Only x and y change. This is the cylindrical coordinate system. So what will be the Jacobian? dou x comma y comma z by dou r comma theta comma z is determinant of derivative of x with respect to r, x with respect to theta, derivative of x with respect to z, derivative of y with respect to r, derivative of y with respect to theta, derivative of y with respect to z, derivative of z with respect to r, derivative of z with respect to theta, and derivative of z with respect to z cap. What we get is derivative with respect to r, you get similarly cos theta and minus r sine theta. And derivative with respect to z, there is no z, it will be 0. Then we have sine theta, r cos theta, 0. Derivative of z with respect to r, 0, with respect to theta, 0, with respect to z, 1. So you can pull out r common, and then when you evaluate the determinant, 1 times cos square theta plus sine square theta is 1. So again it is r. So the integral over 3D Cartesian space of a function in terms of x, y, and z converts to an integral r dash in r theta z space. Function is changed to r cos theta, comma r sine theta, comma z times Jacobian modulus is r and dr d theta dz. So again in cylindrical coordinates, the volume element changes to, instead of dx dy dz, it becomes r d theta dr dz. This is the volume element. Okay. Let us see. I'll try to type something. Volume element. Yes. And see some images which you will understand. Yes, this is a good one. So this is a volume element. This is r d theta. This is d theta angle. This length is r d theta, dr dz. This will be a volume element. So the base will be r d theta will be one side multiplied by dr multiplied by dz. When d theta, dr, dz are so small, they will be considered just like a cuboid. So the product of the three sides will give you the volume. So this is dr, r, d theta, dz. This is a good pick. Good pick for reference. Okay. Now there is something more difficult one is conversion to spherical coordinates. Okay, I'll just mention this. This is more difficult. These two are easier. Conversion of Cartesian coordinates x comma y comma z to spherical coordinates. R theta phi. All right. How is the conversion? It is like this. This is a little more deeper topic of spherical coordinates. I will r sine theta into cos phi. Y is r cos r sine theta into sine phi. And z is r cos theta. This picture depicts the spherical coordinates. So, see, this is x-axis, y-axis, z-axis. But sometimes in problems, the problem is in terms of a sphere. So we define r theta phi like this. R is the distance from the origin or the pole. And then theta is the angle made by this vector joining origin to this point with the z-axis. Okay. Now this axis, this is theta. So this is called as the polar angle with respect to the polar axis. So this is the, and then phi is called as the azimuthal angle phi. The projection of this radius onto the xy plane, onto this plane. So basically you have r, theta and phi. So on the xy plane, and that angle it makes with the x-axis is phi. So based on this, we have this figure. Okay. So this is a spherical coordinate system. And many problems, very complicated physics problems are solved using this one. So volume element and spherical coordinates. So see the depiction of the volume element. R d phi, R sine phi, and dr. So r sine phi d theta. So this is the volume element. So you will get r square sine phi dr d theta d phi. So this is a very difficult one to comprehend. Here. Yeah, this is the figure, spherical coordinates figure. Okay. So This is the volume element. This is a volume element for reference. So how the volume element looks. But for our conversion, we just use the Jacobian, which is tau x, y, z with respect to r, theta, phi as the coordinates. So we can just do this derivative. This is derivative of x with respect to r, derivative of x with respect to theta, derivative of x with respect to phi, y r, y theta, y phi, z r, z theta, z phi. And we get a determinant like this, sine theta, cos phi here. Here we get sine theta, sine phi, and derivative of z with respect to r, we'll get cos theta. And then here we get r cos theta, cos phi, r cos theta, sine phi, and minus r sine phi, minus r sine theta, sorry. And here differentiating with respect to phi, minus r sine theta sine phi, then plus r sine theta cos phi, and 0. So when we evaluate this, I'll not do it. You can try to solve this. The final answer you will see, you will just get r square sine theta. Therefore, dx, dy, dz will be changed to Jacobian times dr, d theta, d phi, which is r square sine theta, dr, d theta, d phi. Okay, so that is what the volume is shown here, r square sine theta, d theta, d phi. So the total, this is the phase multiplied by dr. If you do, you get the volume element. All right. Simple problems, very simple problems, 1 or 2. We'll just do that. I'll just take 10 more minutes. All right, let us now see this. This is problem on change of variables. So this is the first question. So evaluate this integral x comma y dx dy, where r is a parallelogram in xy plane with vertices 1 comma 0, 3 comma 1, 2 comma 2, and 1 comma and 0 comma 1. Using the transformation u is equal to x plus y, v is equal to x minus 2y. So first of all, in the xy plane, it's all positive. So this is the xy plane. This is the region or the domain Rxy. We have 1 comma 0, then 0 comma 1, and we have 1, 2, 3, 3 comma 1, I'll do this way. I'll make this as 1, 2, 3, equidistant 1, 2, 3. Now, the points are 1 comma 0, 3 comma 1, then 2 comma 2, and 0 comma 1. This is 2 comma 2 is here. So this line and this line are parallel, and this line and this line are parallel. Okay. So this point, we can take it as A, 1 comma 0, B, 3 comma 1, C, 2 comma 2, and D, 0 comma 1. Now this gets transformed. How it gets transformed? We have to use a transformation function. So u, let us see. So we have to see the xy transformation. To u is equal to x plus y, and v is equal to x minus 2y. So first point is x is 1 comma 0, xy is 1 comma 0, 3 comma 1, 2 comma 2, 0 comma 1. So these are the points A, B, C, D. How do they transform? X plus y. U will be 1. Here for B, U will be 4. C, it will be 4. For D, it will be 1. Next for V, it will be x minus 2y, that is minus 2. Then, no, sorry, this will be 1 minus 0. So it will be 1. Then 3 minus 2, it will be 1. Then 2 minus 4 will be minus 2. And 0 minus 2 will be minus 2. So this is the transformed coordinates. So transformed coordinates A dash, this is A dash, B dash, C dash, D dash. Now A dash is equal to 1 comma 1. B dash, the transformed coordinates, UV is 4 comma 1, C dash is 2 comma 4, and D dash is 1 comma 1. Sorry, sorry, I'm writing all messing up. It is 1 comma 1, 4 comma 1, 4 comma minus 2. I'm sorry. And D dash is 1 comma minus 2. So in the UV plane, now let us plot the UV plane. You have negatives also, so let us plot like this. This is U, this is V, this is R UV or R dash UV. A dash is 1 comma 1. So 1, 2, 3, 4. And 0, 0, 1, 2, 3. And minus 1, minus 2, minus 3. And then 1 comma 1 is this point. 4 comma 1 is this point. 4 comma minus 2 is this point. And 1 comma minus 2 is this point. So that parallelogram is also this. This is also a parallelogram, but this is transformed like this. Now, we don't have to worry about this physical transformation. This is graphically, I've just shown how this is a transformed region, but we want to find this integral. What we need to do is to find the Jacobian. U is x plus y and v is x minus 2y. So Jacobian of dou x comma y with respect to dou u comma v is partial derivative of x with respect to u, and with respect to v, partial derivative of y with respect to u and with respect to v. So this is 1. Okay. So this is u and v in terms of x and y. So x and y should be written in terms of u and v. So we'll have to convert this, solve for x and y, subtract. U minus v will give us minus 3 plus 3y. So y will be u minus v upon 3. And x will be equal to, multiply this by 2. So 2u plus v, that will eliminate v, but that will give us 2u plus v will give us, that will eliminate y, will 3x. So 2u plus v upon 3, and y is u minus v upon 3. So this is the transforming function. So we need partial derivative of x with respect to u. So that is equal to 2 by 3. Partial derivative of x with respect to v is 1 by 3. Partial derivative of x, y with respect to u is 1 by 3. With respect to v is minus 1 by 3. So the value we get is minus 2 upon 9 minus 1 upon 9. That is minus 3 upon 9. That is minus 1 by 3. However, we have to take the modulus. So evaluating, what is the integral? Integral x plus y whole square dx dy. So integral on this region x plus y the whole square dx dy is equal to integral on the region uv. Now x will be replaced by 2u plus v by 3 plus u minus v by 3. Oh, so x plus y is already u, so doesn't make a difference. Straight away you can write that, times modulus of Jacobian times du dv. So automatically you get vv cancelled and you get u square. So integral of u square Jacobian, modulus of Jacobian, modulus of 1 by 3 minus du and dv. Let us see. Now u varies from u equal to 1 to u equal to 4 in this transformation. And v varies from, we can see, -2 to 1 along the y-axis. So v varies from -2 to 1. So now we can evaluate this integral. So v varies from -2 to 1. Now this is 1 by 3 u cube by 3 into 1 by 3, 1 by 9, from 1 to 4 dv. This gives integral -2 to 1. 4 cube is 64. Minus 1 cube is 63 upon 9. 9 sevens, 63. So we get integral of 7 dv -2 to 1, which is 7 times v. Apply the limits, -2 to 1. So 7 into 1 minus of -2. 7 into 3, 21. This is the answer. This is an easy numerical question that can come up in the GATE exam. All right, I will end the class here today. You will need to practice this. I'll stop share. I'll immediately upload this. You go through this. Tomorrow, just another 1 or 2 problems, and then I will start vector calculus. Tomorrow's class will be an important one. Please don't miss. So before starting vector calculus, I will take a brief of vector algebra. So vector algebra will be a very basics of vector algebra, and then we move to vector calculus.